So next up we have Ivan Cohen, who's here, and he's going to talk to us about the tricky subject of emulating analog effects in the digital world, which is going to be impressive to get this into 20 minutes. So over to you, Ivan.
And it's using JUCE. So I'm very happy to be here today, to have been invited to the JUCE Summit. And I would like to thank again the Rolly team and the JUCE team for that. And before we start with this presentation, I just wanted to tell you that my slides are actually in a JUCE application that reads a text file containing all the contents of the presentation. I thought it would be useful, so it would be less boring to create the actual presentation to do that. But in the end, I think it's a very good example of trying to do something clever and getting something pointless at the end. But anyway. This allows me to have some cool widgets like this magnificent JUCE logo. So I'm going to talk about virtual analog audio effect simulation. And I'm going to launch my company next year. So I'm very happy to present my work today. Virtual analog audio effects and virtual musical instruments are really everywhere nowadays. It's a term you can see everywhere in all the new products on the musical market. That's something that is widely used by musicians and engineers, and it's also a subject widely studied by a scientific community. We are trying, when you do that, to simulate some things like analog audio effects such as compressors, mixing consoles, guitar amplifier or pedals, analog synthesizer, virtual drums, orchestra, all done with simulation software. There are some examples of these things. And sometimes we do have even virtual players in this software. It's just amazing. So what is a virtual analog audio effect anyway? It's something you get when you're trying to model an analog circuit, and you get some C++ code and a digital audio effect to do that. Simulation can be available as software in plugins or hardware, like here. We are trying to get the similar functionality and sound signature you have with the original ones. And doing so has a lot of very good advantages if we compare with the original ones. For example, you can use as many instances of your plugin that you need, and that's not something very easy to do with hardware. And often the simulations are also less expensive and bulky. But I think there is a question which is really important here. This is, why do we still study that today? Because in the market you can find a lot of simulation software, and we have seen a lot of very interesting things in all the areas related with music and production. But we still have improvements to do in terms of realism and CPU loads. That's why everybody is still trying to get the best simulation. And what is very important for me is that these products are meant to enhance the creativity of people thanks to the quality of sound and familiarity I explained. I think everybody here who is developing software for musicians is trying to achieve that. We want that the users will be more creative using our software. And for me, doing virtual analog audio effects is something you can do to achieve this goal. And I have talked also about familiarity. All the time we have the question, why do we still try to emulate all the hardware or all the, I don't know, guitar amplifiers? And why don't we just create new things? This is because musicians have some habits. And when they use something they really know well, they will feel more creative, they will have more trust in the tools they are using, and they will be, it will be easy for them to be creative when they are using them. That's why I say also that thanks to the placebo effect too, because sometimes they just don't get what is the difference between two kinds of musical instruments or devices. But because they have read somewhere that this piece of software is the best, or this piece of musical amplifier is the best one, they will think that they can be best by using this instead of something else. That's why you can see on the market a lot of emulation of all the time the same compressors, the same guitar amplifiers. And why do we still study that today? That's because there is also a lot of money involved in selling the most realistic simulation ever seen of blah, blah, blah. You can see all this marketing stuff all the time. And the placebo effect might be one of the causes of that too. And personally, I'm doing that because I think this is really fun. This is really fun to do virtual analog audio effect simulation. So, it's difficult to do something in 20 minutes about the subject. I'm going to start by a large overview of what is simulation and all the techniques available to do that. And then I will try to be more practical. The first thing we have to see is that we have various classes of modeling simulation methods, techniques. And we are going to choose one for a particular circuit we want to simulate, depending on the nature of the system we want to simulate. For example, we have linear systems like a filter, delay lines, room acoustics, and we have nonlinear ones, the ones which had some warmth, some harmonics, like guitar amplifier, distortion effects, or compressors. We need also to see if the system has time-varying behavior, like the chorus, the tremolo, or any effect with a parameter modulated by a LFO. And for all these systems, we have various ways of getting the simulation. We have what I call the black box approaches, which means we don't have any interest of what is happening inside the system we want to simulate. So we are just sending some signals inside, we get the outputs, and using the information we get, we are trying to do the simulation. That's the principle of everything you can do by a measurement of impulse responses and convolution. And you can also do things like that in the nonlinear domain using the Volterra and Hammerstein series, which are a generalization of convolution for nonlinear systems. And you have the white box approaches, like physical modeling. There you will really look for what is happening inside the system, and you will try to put into equations all the electronic components interaction that are happening inside the system. And of course, you have what I call gray or hybrid approaches, where you are using techniques from both the approaches to get the simulations. And then we still have another way to categorize the different methods. We have what I call general digital signal processing methods, where you try to mimic all the functionalities of your system, the system you want to model, with a combination of transfer function, filters, wave shaping. We try to take each function achieved by the system, and we try to simulate it with a few basic operations. Or, if you want to do really physical modeling, you have all the methods using the Kirchhoff laws, which are basic electronics theory. And we are going to see more in detail what is called the K method and the state space representations. Globally, when you are doing physical modeling, you have to follow these steps. you have a circuit schematic. You try to generate the equations of this circuit in the real world, in the continuous domain. You do the discretization, so you can put these equations in the digital domain for a given sample rate. And then you have the simulation engine, which solves in real time all the equations. You can add a few things there, like all the mathematic component models you are going to use. I will say more about that after. You can try to simplify a little the circuit schematic you are going to model, because in the analog world, there are a lot of things happening that are not very interesting in the digital domain. For example, a typical example, you have sometimes some capacitance which are meant to remove the DC component of the input signal. In the digital world, you don't need to do that in the same way than in the analog world. So you can just remove a few components from the schematic and get something more simple to simulate. And that's where this thing is going to be very helpful. You can use some software to do an automatic generation of the equations from the circuit schematic. You just enter the net list of the schematic, and then you can get all the code or the equation to do all of that. And at the end, you try to do some optimization everywhere to improve the realism of your simulation, reduce the CPU load. And so, it's very ugly, but actually each time you take a schematic and try to do the simulation, you get some equations that can have this form. If you know exactly what is inside these matrices, and if you know all the component models which are embedded in this term, you can just solve these equations using these methods. And you can get the sound of your simulation, which is represented here. The simulation is just a matter of finding these matrices and solving these equations in real time. So we're going to be getting started into how to do an actual simulation. So the first thing I have to tell to you, if you want to do some simulation, and if you don't know at all this stuff, is to look to all these information sources. You will be able to see how people is doing it, get a lot of information, and obviously I will share the slides after, and you will be able to get all of this. And the first thing we must do when we do a simulation is to get some studying tools, because before you start to using all the techniques I'm going to present to you, you have to know exactly what your circuit is going to do to your signal. So when you will be at the end of the process, you will be able to see if your simulation works well, if it does what is expected. If you want to model a low-pass filter and you get a high pass at the end, there is something that is wrong, obviously. So it's a good idea to start by doing some study, for example, with SPICE simulators in general. You can just draw the circuit here. You can send all the signals you want inside your circuit, and you will get an output simulated in the best way possible. You can even send some wave files with a software called LT-SPICE, which is very useful. And you can use also some software like MATLAB, Python Maxima for what I call symbolic study. So you can debug everything you do in the process from the generation of equations to the simulation. And then you need also to stay in the real world to use some measurement devices on the original circuits. So you can see if SPICE and your simulation is really doing the same thing than the original circuits. Here is a magnificent device I have developed with the company 2Notes to create some new models for vacuum tubes. And it was very useful to achieve maximum realism. And as I said before, we need some mathematic models for all the components, like resistances, capacitance, inductors, output transformers, and having measurement devices in the real world is very useful for that. And in JUCE, it's very easy. Oh, it's ugly, that. It's very easy to do the audio part. You just need to create a new plugin project with the Projucer and enter all the simulation code in your audio parameter class functions. But sometimes you will need also some extra C++ libraries to achieve a few functionalities, like oversampling, resampling, interpolation algorithms, root solvers, and you will need to get some third-party libraries like this one, or you might need the upcoming JUCE 4 DSP functions. So I'm going to show you an example of circuit. This is a diode clipper with a low-pass filter. This is achieved with just one resistance, one capacitance, and 2 diodes. It's something you can find in the MXR Distortion Plus pedal, for example. And it's a simple circuit, so it's well suited, I think, for presenting you how we do that. And this is the nonlinear static transfer function of the diode clipper. But doing the modelization is not just taking this function and doing some wave shaping. You need to consider also the interaction of the other components with the nonlinear static transfer function. And I'm going to show you how we do that. So we start with the diode model, which expresses the current going through the diode depending on its voltage. This is the equation you get with the Kirchhoff laws from the schematic we have just seen. We put that into a state space representation. There is nothing fancy here. It's just a representation very useful to do the simulation and to solve in the digital world. We just have some variables for the state and for the input and the output. And this is it. With that, we have already the model of our full schematic in the continuous world. So now we need to go to the digital world. And we are going to use what I call integration methods, like trapezoidal or BDF2. It's just something we do from the equation we have seen just before. And just by doing that, we can get all our outputs. And sometimes we have something called transcendental equations. It's when you have some nonlinear expressions you can't explicitly write. You need to use a root solver to get the result of your equation, to get the output people will be able to listen to with your software. And doing this isn't difficult. It isn't easy to write that in C++ code, but it's very expensive in terms of CPU load. So what we do in general is to use lookup tables computed offline with the Newton-Raphson method. And then we just have to apply some interpolation algorithms to get our outputs. And this is the code we get, for example, for that, with a very simple linear interpolation. What we can see here is just the code that does the audio processing. And then I'm going to do some audio demonstration of that, so we will be able to listen to the results. So, this is just guitar without any effect. Now I'm going to add the diode clipper. some cabinet impulse response, and we can do also that. It's audio time. And I plan to do also a presentation about another filter, but I did not have too much time to do that, so I will just make you listen to the sound you can get from this circuit, which is a low-pass filter you can get in this famous synthesizer. So here is the sound without any effect.
JUCE.
I had that stuck in my head for 2 days. And so we have seen a lot of things there about how we can achieve some simulation from any schematic. I will share everything and some source code also on GitHub, on the JUCE forum, so you will be able to see how that works and you will be able to try a few things. I just want to say that there are a lot of things going on right now on this area in the scientific domain. Some people are still trying to get more realism from their simulation. And we have a lot of new techniques to replace the lookup tables also, to reduce the CPU consumption of the software using neural networks and nonlinear regression, which are very interesting. We have some people working on software to get very quickly C++ code from any netlist. We have more and more complex methods for the components and the circuits, some care on the user interfaces. And there is something called pure Hamiltonian systems, which is done at IRCAM, which is very promising. If you are interested, you should check this out too. So thank you for your attention.
Lovely stuff. The mathematics went way over my head, but anyone who writes their own slide viewer with embedded things that play audio, and that gets points in my book. Any questions?
Would you be able to use similar techniques if you wanted to create a virtual analog synthesizer?
Mm-hmm. So you mean for all the generation of signals or so? That's not something I do a lot for now, but you have a large amount of techniques too for that. I think if people here is developing synthesizers, I will be able to talk about that better than me. But I know that some people are spending a lot of time measuring the oscillators, for example, for each synthesizer they try to model. And they try to generate curves that can be as similar as possible as that. And you have also some special care on all the envelope generation stuff, and it's complicated to do.
Questions?
That was fantastic, thank you.
Thanks.
It's quite a long process, I guess, to model something. So you were talking about the simplification step. So what would you initially try and simplify, and what would you definitely not simplify? For example, your tube model you showed. Is there a process in there you would just, let's not do that, let's focus on this section?
So about myself, I did a PhD thesis about guitar amp simulation in the past. And obviously, there is a lot of things going on in guitar amp in general. And the first thing we do to be able to have something in real time is to divide all the section in the guitar amplifier in blocks. And we simulate each block separately of the others. And then we are using some techniques to model the coupling between these blocks. And often these techniques are not perfect. So the first thing we simplify is the interaction between these blocks in the guitar amplifiers. And then we have a lot of things we try to simplify in the component models. For example, at first the output transformers will be linear instead of non-linear. We will try to simplify some things going on in the power supply. And you can simplify everything if you want. And the process of creating a good simulation is first simplifying a lot of things and then adding a few things one by one until the sound is good and before the thing is not possible to be used in real time.
Thanks again.